to a full wall, and how much it has to go through a wall on the other side. We assumed 10 dB, 10 dB, 10 dB, and then another 10 dB on this side. We assume 10 dB per wall is 900.
Oh, okay.
Right. So if it's not going through each wall, if it's let's say on this wall, there wasn't really a brick wall there. It was just kind of something else, or it was at the edge of the building and it could see around the building, then you might not get the whole loss in here. That's why I'm saying it'll be somewhere between 0 and 40 dB of delta, probably between two equidistant buildings that one is a direct line of sight and the other one is going through two buildings in order to get to the guy. So that might be 40 dB of delta. So now, this is all related to power. We haven't talked about interference yet, right? We haven't talked about what happens with noise, what happens with this is assuming everything works exactly as you want. So you have to make yourself aware of performance expectations from the vendor. So in addition to the table that we just talked about of what you need to know from the vendor so you can start planning your network, we said you needed antenna gain numbers, right? Things to know, or things you need to plan and debug your RF network. We said antenna patterns, right? This was one thing. You needed to know TX powers and the accuracy, with the accuracy. And something we didn't talk about yet, which is too much for today, the TX mask, which means what is the character, or we'll just call it the character of the transmit. Character of TX. And then you need to know your RX performance, which is the one I want to talk about now. RX performance. So the RX performance, what I want to focus on with the RX performance is, let's say someone tells you that you have received a minus 70 dBm signal. What does that mean for how good my performance should be? Should I be able to do 50 megabits per second with minus 70? What's my MCS, my modulation and my coding scheme that I'm capable of performing at with minus 70 dBm? It's not enough information just to determine, but it's a start to say if I was at minus 70, what would my performance be? So the RX performance I'm asking for is, it's going to tell you something like this. This is the performance table that I'm telling you you should have. So you will have something that says your RX power in dBm, and sometimes they call it RSSI, the received signal strength indicator. And then you'll have something else that's called, depending on how sophisticated the network is, or the device is, the center or the signal to noise ratio, depending on what they want to give you. MCS, and then throughput.
Signal to noise ratio.
I'll talk about them each in a second. So this is the kind of table that you'll have, and I'll define them each soon. So let's say that they'll tell you anything better than minus 50, expect your center to be like 40 dB or something. Your MCS, you'll be at the best. You'll be able to do 64 QAM, 5.6, for example. And then your throughput will be 100 meg if you wanted to test it, for example. Okay. And then they might say when you go to minus 60, it'll only be 30. If you go to minus 70, it'll be 20, minus 80. And there's a whole bunch of points in the middle. It'll be 10. And then maybe they'll tell you minus 80, minus 90, minus 85. You'll have 5, and this is your ultimate sensitivity. Don't try to, you won't be able to get a signal below that. Just say that. All right, and here maybe someone will tell you this is 64 QAM still, but you're not doing 5.6, you're only doing half. And here maybe 16 QAM,
This is a French for us. بدر بس ماشي.
I'll explain it in a second.
Yeah, but it's okay.
16 quam, maybe.
There is no test after this.
3/4. Who told you that? And this is like QPSK, 3/4.
It's in the lab.
QPSK, 1/2. So maybe this will give you 80 meg. I'm creating numbers. This is a system that could exist, but
You're
maybe
taking
doesn't.
your word for it.
50 megabits per second. This is maybe 20, and this is maybe 5 megabits per second. Okay?
Okay.
So, this is a typical receiver type of performance that you would use to judge if your system is performing as you expected, or did I just receive a hint that there's probably interference in my system. So what do each of these guys mean? This is your RSSI level. So you can ignore the first column, or the second column for a second, and assume that this is an interfererless, noiseless, it has its own noise only from thermal that we talked about last time, the KTB noise, if you guys remember. Let's assume that the center is not there. We won't talk about it just yet. But if you had a certain RSSI, someone has tested in the lab the performance of the receiver, and it performs as expected. When you're anything above minus 50 dBm, he's able to get the best modulation coding scheme that the radio is capable of, which means, you can do 64 QAM, and we talked about this, I think, once before, that's how tightly you can pack your data bits in every transmission. So if you're doing 64 QAM, remember maybe we didn't talk about it here, but it's maybe too much to talk about at this time, but let's just say it's the most efficient way to transmit. But it requires you to be, so far, based on what we've just talked about only, at a really high signal level to get it. So if all of your devices were at minus 50 dBm or higher, and there was no interference in the area, you should be able to share 100 megabits for throughout the network. Any one of those devices should be able to do 100 megabits per second all by himself, if he's at above minus 50, for example. This is the table you would ask them for. Give me your RSSI versus throughput and MCS and center. Tell me what those should be. And they would give you this table. Or you pull it out of their spec sheets and find this out. And then you can go, it's like, okay, wait a minute, hey, I'm at this radio. Hey, this is Adi. Assalamu alaikum, hey man, I'm having trouble with this radio. I'm only, I'm doing this link test across it. I'm doing the speed test just to verify this link. I connected up a device between one node to the other. These guys are only 100 feet apart, and I should be getting minus 50 according to my calculations, and I am. I'm getting minus 50 dBm, but when I run a speed test across it, it's only telling me he's got something like 20, 25 megabits per second. What's going on?
Where I should have 100.
Yeah, where I should be getting 100. This thing says minus 50 should give me 100, but he's only getting 25. So he verifies, yeah, it's getting minus 50. But I'm not able to get my throughput. What's going on? So then he'll say, okay, wait a minute. If it's getting 25, I'm going to take a big guess here. It's only getting 25, somewhere in here between 50 and 20. Then most likely his center, or his signal to noise ratio, dropped. It's somewhere between 20 and 10. 20 and 10. So now what do these numbers mean? So as I said, real high level, this was just power. MCS just says how tightly you can pack your data. And you can pack it more tightly when you have less interference and less noise. Noise comes with power. As you bring power down, you get closer to noise. Remember we said noise floor last time? If this was your noise floor, we didn't have a chance to draw it, but we were kind of hand waving. If this is your 20 megahertz signal, and this is the noise floor that just comes from KTB, and we'll just call it that. This is just the noise floor. This is the noise floor. This has nothing to do with interference just yet. Your noise floor. This is what your receiver generates as noise just by having resistors and active devices on the board. He's down here, and if I'm getting a signal at minus 50 dBm, so he is, and let's just give an example. Let's say the noise floor is at minus 95 dBm for now. So if the noise floor is at minus 95 dBm and my signal is at minus 50 dBm, that means that I have, at this time, signal to noise ratio of minus 50 minus the minus 95 my signal to noise ratio, my signal is 45 dB above my noise floor. Right, for this one, my signal to noise ratio says that I'm 45 dB above my noise floor. So that's signal to noise. The carrier to interference plus noise, or signal to interference plus noise ratio, is different, because now we're saying it's not just the noise problem from my own receiver. There's interference and noise coming from somewhere else. So this red one is my own noise floor here. But let's say that somehow now someone else is transmitting on my same channel. Someone's transmitting on my channel, and he introduces some interference here for me that way. So let's say that this guy's level here is, say, let's make him higher to make a bigger problem. Someone else is transmitting on my channel, and let's say that he comes in at minus 70 dBm. This is my interference. My interference. So now my carrier to interference plus my noise ratio, the interference is way above the noise. And I want you to do this exercise later to convince yourself. If you were to add minus 70 dBm and minus 95 dBm, I'm going to tell you the number is going to be minus 70 dBm. It could be very close. Because when something is 25 dB below something else, remember we said 10 dB means something is 10 times lower than it in magnitude. 20 dB means that something is 100 times below it. So that means, like, if I had something that was 1 watt, something that's 20 dB below it means that that's something 100 times smaller than it. So 1 watt compared to 0.01 watts. Not, and if you add 1 watt and 0.01 watts together, you get 1.01 watt. You convert that back to dBm, it's still the same dBm number, right? Because something 25 dB down below, it's not going to impact it much when you add them together. So the center here is going to be the minus 50 and minus 70 dBm for the sake of making it easy. Minus the minus 7. So now my new center is only minus 20 dB, right? So when you're 20 dB, now the thing starts to kind of make sense that, hey, there's some interference here. If you was to do a spectrum analysis, you could find this. So how else would you find this? And how would you verify this? The way I would verify it is I would turn my devices off, my devices. I would turn my transmitter off, and then get my spectrum analyzer there. Most good devices would have a built-in spectrum analyzer. Why? Because if I was going to say, hey, I'm on this pole here, and here's the other pole, and I'm looking for the throughput between them. This is where I see minus 50 dBm on both sides. But instead of getting 100 meg capable, when I do a quick test, a speed test on them, I'm only getting 20 megabits per second or something like that, 25. Then, he ran his tests here, but if I do spectrum analysis down here with my antenna, it's not there. It's not at that spot. I do spectrum analysis with my antenna down at the base, but that pole, that other radio is up above me. It might give you some indication that someone else is on. After I turn my radios off, if I put my spectrum analyzer down here at the base, it might be able to tell me something. It might show me some of that interference, but maybe it won't, because I'm down here, and the guy when these guys are up 20 feet above the ground, they can see more things. They can maybe hear a guy who, if I'm down here, it's completely blocked by that building. But when he's 20 feet up above on that pole, on that light pole, he's suddenly above the roof of that building. Or he's suddenly able to see from the corner over there that I was completely blocked by this building. Or there's a tree directly in my way, but it's not his way. So you want to know, what does he see? You don't want to know what you see at the base. At the base, it'll give you an idea. Yeah, there's somebody there. There's some frequency there. But if you want to know exactly what you see, you want to use your antenna that's on this pole. You want to see it at that same height so you can get an idea for what he is. Yes?
No.
So it'll give you an idea. But the best thing is to have it at the same height using the same antenna. The other problem with going down here is the antenna. If you use a different antenna, then he has different amount of gain, so he can't tell you exactly how much power you would see if you were using your antenna, unless you know how much gain is in your antenna and how much gain is in the antenna of the device that you're using for the spectrum analysis. You can do it, it just needs a little bit more skill to do. And then you can also, put your antenna that you're using for testing here, put it on a pole and run a cable. The problem with running cables, the cables have loss. They introduce some noise, other noise figure problems for the sensitivity of the spectrum analyzer that you're using. It's best to be able to do spectrum analysis on those devices from the device itself. So turn the power off on both of these guys, turn the transmitters off, and turn them into listen mode, spectrum analysis mode, and you can hear what's going on. And you should be able to see immediately that there's something causing you interference at about the -70. You'll be able to say, okay, I understand. If it's only giving me this much throughput, I know why. There's got to be interference somewhere in the -70 dBm range. There's got to be somebody there. And you'll turn on your spectrum analyzer and you'll see them exactly. So why is this something important for mesh? Why is it that Hussam is saying, I don't believe that when you have 50, let's say if you have 5,000 users online, that you could do this. What did they tell us before? I remember in the one meeting we were with Mel and his guys, they were saying they have, in 900 megahertz, 900 megahertz had, I think it was 26 megahertz of bandwidth available, right? 26 megahertz of frequency spectrum available, right? I think it was. And he said they break that up into 83 channels, right? 83. So if you take 26 and divide it by 83, let's just do it even easier. 20 divided by 80, that gives you 8. The 20 divided by 8 will give you 0.4, right? No, what's 2 divided by 8?
0.2.
0.25.
0.25. So it'll give you 250 kilohertz, right? 0.25 megahertz. 0.25 megahertz is 250 kilohertz, right? So each channel, if you have 83 channels, each channel can be 250 kilohertz wide. Probably good enough to support voice in most cases. In all cases, good enough to support voice if you want to do voice, but they're just sending some data, right? So
That's why he said they're not using it for radio. For nothing.
yeah, it's just very small communication for
Very
the
small
control.
communication.
Yeah?
Yeah.
And depending on how often they send, if they don't send this very often,
They send it every 4 hours.
every 4 hours.
Yeah, they report every 4 hours.
Okay, so let's just do some rough calculations here so you can get an idea of what's
But
going on.
last thing he said every 5 minutes.
Every 5 minutes.
Yeah, he jumped from 4 hours to 5 minutes.
So let's just
Little meter reading.
Yeah,
Yeah.
smart meter.
Small meter.
so let's there's a lot of things. Remember we spent a lot of time last time talking about how to deal with interference.
Yeah.
What we said, people talk about interference in lots of different ways. One, you can deal with it spatially by shrinking, your directivity. When I talk to one person, I only want to talk to him. And I can switch if I was a really smart antenna, a really smart system, kind of like MU-MIMO, multi-user MIMO, what people call it today. If I decided I want to talk to Sammy, I'll make my antenna so narrow that I can only hear Sammy. I'll put my blinders on, and when I want to talk to Hamad, I will just switch over and I'll just talk to Hamad. So now Sammy is blocked from here. I can't see Sammy, Sammy can't see me. So one way of dealing with interference is by being very directive and talking only to who you want to talk to, spatially separating them out. Another way we said that people deal with it is by scheduling. Right? So you can schedule and say, I'm going to tell you guys not to talk until I tell you to talk. Whoever wants to talk must raise their hands, and I will decide who I will tell you who talks and when he talks. That'll prevent interference from my network. So even though I have 83 channels, well, we didn't even talk about the channels, but let's say, so I can decide, we have a room of 6 or 7 guys, 8 guys, and if everybody wanted to talk at the same time, we wouldn't understand each other, but instead I'll tell you, okay, you tell me when you want to talk, and I'll tell you go. You wait. Someone else is talking, finish talking, okay, next person, who is next? I'm keeping a list and figuring out based on, who raised their hand first and who I think is more important, who might have a better question, who paid me more money. I might let him go first, who has more important data to send to me. I start prioritizing people, and that's how I prevent interference. Another way, so that's for those systems that are kind of listen before you talk, your Wi-Fi kind of systems. It's like scheduling people one at a time, waiting for them to talk. In the past, as we said, the old Wi-Fi, the standard Wi-Fi is people just listen. If no one's talking, start talking. But the problem was is that all of you guys had to be able to hear one another in order to know if that person is talking. Yes, I might be the controller, but in the old Wi-Fi, the base station wasn't very controlling. He was acting like he's just one of the guys. He's one of those friendly parents who was just, hey, I'm just your friend. So he would just say, okay, go ahead, everybody talk, just listen. If nobody's talking, go ahead and talk. Very, very loose. The problem was that there was some guys who couldn't hear each other because there's a whole bunch of trees between this side of the sector, you two brothers over here. There's a bunch of trees and buildings between you, so you can't tell when Sammy's talking. So you're going to talk because, hey, I don't hear anybody talking, so I'm going to start talking. You'll talk to me, but Sammy was already talking to you. You just didn't know it because I didn't tell you anything. It's up to you to hear everybody else. So the scheduling was a problem. So now what if we add this new thing into the mix? There's multiple channels that are available. You can listen if you were really powerful as a processor, and you didn't have, and you had a lot of time to decide when to send your data. If you had a lot of time to think about it, meaning 5 minutes or several hundred milliseconds. I mean, to give you an example, like something like LTE, something like WiMAX, something like standard systems that people put together today. We're looking for turnaround latencies when the system is not overloaded. You're looking for latencies that'll support VoIP. And so you're typically thinking about keeping your latency down into the, something for sure less than 100 milliseconds. People start getting nervous today when they see latency climb about 20 milliseconds of round trip latency. To schedule somebody, let's say there was 100 of us in the room, and you say to any one user in the room, what's the longest time that it takes to send and receive a packet? If I just wanted to ping Sammy, how long would it take for the ping to go and come back? Or how long would it take for me to just send a little bit of data for his voice to come back? If it's anything more than 20 milliseconds, people are getting nervous. Really, for VoIP, you don't need anything better than 100 milliseconds, but it's the jitter that you start to worry about in terms of how that varies from user to user. So if I had a lot of time, because I don't care about 100 milliseconds of latency like the WiMAXs, like the LTEs, like the other proprietary systems that people come up with for backhauls and for point to multi-point. If you didn't care, what you would do is, okay, I have 83 channels. Wow, okay. So what I'm going to do is every time, just before I transmit, I have a few minutes to figure this whole mesh out. I'm going to let everybody scan, let every one of these frequencies, every one of these APs scan, but I'm going to start locking them down, and then different parts of the network get locked down, and different people are scanning, and then I figure out what is the right configuration of all these channels. And then if somebody is interfered with, their message doesn't go through right away, then you need a mechanism to acknowledge packets when they arrive. You need like a fast acknowledgement method here. So let's say I sent you something, Sammy. I sent you something. If I have to determine and change something dynamically, I need some feedback from you.
Acknowledgement.
I need an acknowledgement. I need to know, did it get to you or not? If I hear nothing from you, that means you didn't hear me. I have to decide, what am I going to do about it? I can send it again. I'll send it again on the same channel before I try to do something different. So I'll send it to you. Again, if I hear nothing, it depends on how much time I have. If I know I have 5 minutes of time, I got a long time to figure this out. I'll try and acknowledge it. If it comes back and still nothing, I can decide to do another thing. I can decide to drop my MCS because maybe there's interference. So I can drop my MCS. Maybe it's an interference problem, so I can drop it and say, I'm not looking for a lot of data. Let me go to the lowest throughput rate. I'll go to QPSK half, and I'll send it to QPSK half. If it's successful at QPSK half, that means, okay, there might be some interference, but how much data do I need to go through this network? The problem with going to these lower MCS rates is, remember what I said, what is an MCS rate? It's packing more data, so you can send more data in a small burst. If I have to send, let's say, the same data, let's say I'm able to send the 200 kilobit, let's just give a crazy number. Let's say I had a meg of data to send, 1 megabit of data. And if I could send it at 100 megabits per second, how quickly can I send it out? It goes out in what? In a microsecond, right? Because in 0.01 seconds, right? If I'm sending at a rate of 100 megabits per second is my rate, and I have 1 megabit of data to send, 1 megabits of data. If I can send it at 100 meg per second,
So 1 millisecond. We need.
yeah. So I can send it in 1/100th of a second, right? Because I'm only sending one of those, one megabit. I don't have 1 megabit of data to send, so it's 0.01 seconds, right? 0.01 seconds, which is 10 milliseconds, right? So something like 10 milliseconds. Is it? Yeah.
Yeah.
So
Well,
1 over 100.
1 over 100 is 1 millisecond.
Is it 1 millisecond?
Well,
Yeah.
No, it's 10 milliseconds.
10,
Sorry.
10, let's just say it's 10 milliseconds, okay?
Yeah.
So it takes 10 milliseconds if I can send it at 100 megabit rate. But what if I have to drop it down to, instead of 5, let's say we were able to go all the way down to 1. If I have to send it at 1 megabit per second, how long does it take me to send it? A whole second. A whole second. If I have to send the data at a 1 megabit rate instead of at a 100 megabit rate, it takes me a whole second to send my 1 meg. So the problem with, although it seems nice because it's very noise resistant, because it doesn't require a lot of signal to noise ratio, it doesn't require a lot of signal to interference to noise ratio. But the problem is it takes so long to send the data. I'm going to hold up the medium for a full
Latency.
second instead of holding it up for 10 milliseconds. So you could do it and drop it down, but what if I can do it on another channel instead? I'm going to switch channels, go to a new channel that's more clear, and be able to send it at a much faster rate so I can get this thing off of my network. See, the thing that we have to study for this Silver Springs network is to figure out what are the real requirements for system performance. What do they really, really need in terms of latency, and how often can they resend data? What have they put into their protocol for safety mechanisms? So when do they switch channels? When do they drop MCS, or do they drop MCS, or are they only focusing on a system that changes channels? And what are they doing in the background? They have to be rescanning all these channels all the time, rescanning which channel is the best, and then he reuses it. But not everybody can be rescanning at the same time, right? Because if everybody turns their transmitters off, and then everybody's doing a scan, then they don't hear anybody. But maybe something really smart for them to do is that maybe they're always sending out beacons from every radio. Is always sending out beacons at a certain rate. Maybe every 100 milliseconds they're going to send out a beacon to let everybody know where they're at, which is the way I'm sure they're doing. They're sending out some kind of a beacon on a regular basis. Why? That way the scanner, so you send out at a certain rate, but it's got, let's assume we were all synchronized. If everybody sends out their scan at the same time, and then everybody sends out their beacon at the same time, and then we scan, are we going to hear anything? We won't hear anybody. So somehow they have to be offset in time, so that when I scan, I know that most everybody else is transmitting, so I know who's transmitting what. So I know that all these other frequencies, hey, I can hear him at minus 50, I hear him at minus 80, I hear this frequency at minus 90. The one with the best signals, the guy at minus 90, I'm going to also transmit at minus 90. Because if the floor is at minus 90, then if I'm at minus 50, I've got 40 dB of signal to noise ratio if the floor was at minus 90. You get it? So if he determines the noise floor is at minus 90, somebody hears the floor at minus 90, that means that if he knows that he could receive his own signal from a guy who's right next to him at minus 50, then he's going to choose him because the next guy, the next lowest guy in that same frequency was at minus 90, he's going to have a really good signal to noise ratio. He can use him as a channel. So there's an algorithm in the back working to get everybody to send something so I can hear everybody and figure out who is what, where, and when. And if they're all sending at the same time, it's going to be a problem. So they have to somehow synchronize them and let them listen for, not synchronize them, keep them out of sync. So they can transmit at different times so he can hear everybody who's possibly around in the area. They could do something even more sophisticated. They could keep track not only of the power, if they wanted to, but they can keep track of the MAC addresses. Since this is their own system, they can say, okay, I heard MAC address X, Y, and Z. He was at this level. These guys don't move. They're not moving around. This is a fixed network.
There is no handovers.
There's no handovers, right? There's no, these are fixed devices. There's no mobility here. So if I hear this from this power from this guy, the only thing that can change is foliage. All right, so maybe in the winter, he might get a higher power level from that guy than he hears from him in the summer. We've had plenty of problems like that where someone deploys their network in the winter when there's no trees around, and then suddenly, you know, spring comes around and it's like, hey, something's wrong with your radio. It doesn't work when the temperatures are hot. You have a temperature problem with your radio. It's like, no, I think the temperatures are fine. It's the foliage you just, in the spring you deployed it, or in the winter, there's no trees. Now you got, because he says, we got 10 dB, 15 dB less power. That sounds like an evergreen tree. 15 sounds a lot like an evergreen tree, but you don't have evergreens that are going down and up in the winter, so maybe you have some kind of deciduous tree that, you know, grew its leaves or something. So in any case, so they're doing something like that by managing, by understanding themselves. No matter who you talk to, it's like the more you know yourself, the better, right? So this network, the more it knows who of its own clients are out there. Over time, I mean, just think about it this way. If there was 100 people in this room, if we spent enough time with each other, asking pertinent questions about each other, we will eventually know each other. And if all of us stay kind of in the same, we don't change over time, then we'll be able to figure out how we're going to deal with each other on a regular basis. You know, that guy talks really loud over there, so try not to use his frequency. This guy's loud. He's try to talk on a different wave, like how the heck behaviors. This guy likes to make fights, so argue with people. Talk on a different wave. Don't talk to him on his wavelength. Talk to somebody else if you want to talk about that topic. Or you have to raise your voice a lot if you want to be around that guy and have him hear you, or have others hear you because he likes to talk really loud. You'll learn. And so there is this learning process that has to happen in Mesh if you want to deploy it correctly, to figure out what it is that you want to do. Any questions about this? So this is the table that you should for sure get from other people. And if you want to watch the video now, we
Yeah,
skip
please.
time for the video.
We want you to sit down, inshallah.
Yeah, please.
Get
Any questions on what we've talked about so far, guys? I know it was.
Other than it's a French, guys.
No, you
Next time,
don't really need to know
we'll
this column except to know that they're going to give you this type of column.
Yeah.
The higher the modulation and coding scheme, the better, the more efficient you will be at sending data. We gave the example of 100 meg versus the 1 meg.
Here you go.
No. Oh, you want to put it on something? Actually, we put it on the projector or should we something?
المشكلة
Yeah, we can do it if you just give
كيف
me.
نقدر نشبكوا على هاي على بروجيكتور؟ Let's try to.
No. I got the Apple TV.
You get it?
Yeah.
Okay.
Yeah, you can
It's
play.
much better and easier.
I بقول لك challenge me, man. He's saying make sure you challenge me, guys. أي والله بالنسبة لي تبلش فيه. Probably the first one is 1 minute. I put it on.
This one I saw.
Okay, that's good. That's good. Okay. This is the 1 hour.
تجي من تحت مراد.
بلش انت رح figure something. والله أشرف try to get this to work الله يرضى عليك خليني أشبك لك هنا. هذا بروجيكتور. See if we can hook it up to the iPhone.
ايفون بزبطش بدك بالابل تي في يعني.
ما بزبط
بدك الابل تي في.
هذا المفروض يكون فانسي الله حريقه. $700. أبي التي في هي.
وبدك الابل تي في عشان تعمل انترفيس.
طبق هي.
شو اسمه؟
Just we have to figure out the inputs.
No, fine.
TV.
حط على الاتش دي ام اي. خلاص. شغل الابل تي في. The problem is you didn't have wireless between
They
your.
have it in the building.
Oh, they do.
We can do hotspots.
Or you can do like ad hoc or something.
We have a large monitoring system called Redscape. We use a lot, thousands and thousands of these things. Silver Spring, big discussion. We don't think so. So our particular average customer.
سرايا كافيه دور كيس. Technology specialized
Sam, I have to leave at in about 20 minutes.
Okay. No, بس we want you.
Yeah, but is there a place that you think is most important for us to go and see?
Oh.
When المكان اللي كان most interesting or كان confusing to people that you want to?
لا مش احنا بدنا بس عشان تتفرج عليه على اساس انه if we can if you think انه في شيء important to touch base with it.
It's
I will send it to you. I will.
yeah, we'll spend like 1 hour.
It's
لا 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 20 minutes. That's fine.
CAFE.
Where's the area, or who else is here for you guys to figure out some questions that you think they ما فهمناش علينا ما حكى X, Y, or Z.
معنا نشوف بس نخلي حسام وزكي نطلع لك على سكشن ونقول لك انه والله go to يعني 50.
Oh, بدك تبعت لي اياها ده انا
بحاول ابعت لك اياه كمان.
ليش ما ضبطش يكون فوت على شو اسمه؟
سراي اللي هو SARAYA.
ما كان يطلع هذا. لا ما كان يطلع الفيديو هذا.
Right here, right here.
كل
آه.
الفيديوز طلعوا ما علينا. لا لا.
Clear, just clear.
Yeah. So SARAYA. And
So anyone want to guess why did they think what was the thing that we were controlled by?
Right. Yeah, but you're right. We have to figure out which one. It's a long lecture.
بنحاول احنا هاي ننزلها عشان هو يتفرج عليها براحته.
احنا ممكن الحين بعد ما شاء الله نمشي
اه بننزلها. We have to put it down.
yeah.
ايوه.
Let's go back.
بدك تعمل airplane or something?
Yeah, you have to mirror it from the phone.
Okay, he has to join the network.
Yeah. Okay, so now you have to hear from the phone.
وين شو بدك تسوي؟ يا شو بدك احكي لي شو بدك تسكره؟ طب لسه ما عم نشغل
الله
الصوت
يخليك. خلاص should transfer right away. يطلع لك.
مش طالع السكرين هاي صار شوي.
Something changed.
Yeah.
No, I think that's my pictures.
هاي شكله بده يشتغل. ايوه ايوه
Yes.
Yeah.
اوكي. الفاليو. هاي شغال.
From the TV.
عندي والله.
When you get down to the level that we're at.
بس خلينا نقفل لك شوي.
You tell me where is a good spot.
Yeah.
Tell us
Okay.
where is a good spot.
What we do, and you'll see this in
What they do. Which is a good spot.
Okay, so you-
use a cell backhaul for as many as 5,000 to 7,000 meters. So you reduce the monthly charge per meter to about a tenth of a cent, to a half.
Okay, so you guys understand. So
Per month, per meter, as opposed to $5 per meter or $10 per meter when you have 4 million meters. It gives me a lot of pulling in on a basis.
you guys
Now, the cell
so
carriers are trying really hard to get that everything. But if you look carefully, part of what they're doing is they're trying to extend the life of the tree.
so what he's talking about is like what they could have done with these meters is to have everybody connect through a phone line. They would have to run phone lines to each meter,
Right.
and they're gonna have to pay a monthly fee for.
That's what he was talking
They
about.
got to run, like which is, so they would have to run phone lines, to get the data
Wired,
back and
yeah.
connect it back. Or they could do is what Silver Spring's old business used to do, which is using cellular network. They would put a cellular modem in each of these, and whenever they want to send, they would use the cellular towers. They would talk to a cellular tower. It's a really reliable network, and that's why they loved it.
Yeah.
Right? Is because the cell people did all the work for them, and then 99% of the places they go, 99.9% of the places they go, it's covered.
Yeah,
And so they didn't have to do too much, but there's a monthly fee.
yeah, monthly fee. So
Right?
this is one
So they
issue.
got rid of it. So they
Yes.
said, okay, now they finally discovered that we're gonna do things wirelessly on our own network, something we own. We don't wanna pay the cable company, we don't wanna pay anybody. We'll do these networks here, which is all internal, they just put their devices there. And then what remains is one problem. Okay, so they can connect these devices together, how do they get that data back to
Yeah, you
their-
need like a controller or something like that.
They need something like that, so they would use a backhaul, again, use a wireless backhaul. Either they would use, like I said, if they wanted to pay just for that service, they could maybe use some cellular data network.
Right.
Or they could, if they wanted to be totally free still, they'd buy some equipment from any provider like like our company or Motorola or whoever they wanted to buy it from, a backhaul. And they would aggregate all that data back at one point from all their APs and send it back to their network operating system somewhere else. Then they can pay for fiber or whatever they have to pay for just in one place, and they don't have to pay for it in two places.
So they're trying to say, oh, we'll give you a super deal on 3G without all the modems. But utilities want those things to last for 20 years. I'll show you some of the things we go through to allow you to upgrade your firmware over the air, to be able to add new features on the fly. Because we know that utilities are going to say, I don't want to change that meter for 20 years. What cell phone technology is going to last for 20 years? I guarantee it's not going to be 3G. So that's kind of the challenge that you have with cell phones. The other thing is just coverage. Because if you don't have coverage and you're using your cell phone, you just like in here, this room is very bad. You walk outside.
Yeah.
Well, but your meter can't walk outside, so you're kind of stuck with the meter. What are you going to do? So those are kind of some of the reasons
Well,
why.
where do they install these? I
private,
thought they were outside.
using
No,
private
those
frequencies.
meters installed in the houses.
Like unlicensed frequencies.
Like,
Okay, so here's
Like
what
a
Silver
water
Spring
meter.
kind of
The
called.
water meter's inside. I know.
No,
I thought
actually, this is just,
So we
he's
use-
talking about just the electrical. They only doing the electrical.
Yeah, they don't deal with water.
But the electrical meters are already outside. Are they going to change what ComEd does today?
No. If it's outside, then they're gonna keep it outside. There is some of them inside, so they have to go.
I didn't know
inside.
that ComEd. Do they really have meters that are
Yeah,
inside
yeah,
today?
yeah, yeah,
Anybody
مثلا
know
بالعمارات
Yeah.
it's inside. بعمارتنا مثلا inside.
It's inside, really? Or?
اه طبعا في منهم
مش
inside.
inside الدار يعني جوا تحت مثلا بالدار
أيوة، مش
بدك
جوا،
تكون-
مش inside
بس
all
بدك
the
مفتاح
way.
تفوت وكذا.
Oh, really?
زي الالكتريكال روم sometimes
Yeah,
they
the
put them
electrical
inside.
room, yeah.
Oh, for like for business.
Yeah.
For services, زي services room, yeah, electrical room pretty much.
Okay, I didn't know that.
Yeah.
That's new.
خلونا let's come to this table all of us أو نيجي هنزل وريتكم.
طب ليش ما
The
فكروا
same
مثلا
radio in different form factors. For metering, for monitoring and controlling the electric grid, for doing work in home with energy efficiency. Demand responses, little switches on pool pumps
Bring those things,
and
yeah.
on other devices that utilities can turn off during peak times of the day. They'll give the customer a rebate for doing that, and they'll save energy just at those pools.
Watch it. Put it here.
We also have smart thermostats where the customer can set a temperature based on the price of electricity. We will the network to set the price of electricity for that hour for the thermostat. And then your thermostat will make a determination as to what temperature you want the home, raising or lowering the temperature to adjust air conditioning in most cases, so that you can save money or be cool. It's your choice. And then the new emerging area is electric vehicles and PV, which is for control of those managing. And these
Yes,
are
yes.
applications include streetlights.
بقدم هاي الطاولة نحطه كراسي هنا وهنا.
That's